I guess you guys now you see my screen, right?
Yes.
Right. So I'd
Yes.
like to go back to determined versus indeterminate, because this is going to help us to understand what is this about, what is this force method for beams, what is the purpose of having it, and what's going on here. I'm gonna go here, just gonna skip the three, gonna say indeterminate versus determinant, right? So I'm gonna say for determined versus indeterminate, we have this number of equations. So for each structural member, so we're gonna say here 3 times n y3, because I have 3 equations, summation of the force in the x, y, and the moment is gonna be equal to 0. So I have here 3 equations, and I have here number of reactions. And if number of reactions gonna be the same as number of equations, I'm good. It's gonna be determinate. I should be able to solve this problem. If number of reactions, which means unknowns, is gonna be more than equations, it means indeterminate. And the degree of indeterminacy is gonna be equal to R subtracting 3n. We went through this already. Can I give you here some examples? I have a couple of examples that I'd like to show. First example, I have fixed beam. So here's a beam. At one end is gonna be fixed, at the other end is gonna be roller. I'm expecting here one reaction. Here is gonna be another reaction, the y direction. A reaction here, because of this fixed, I'm gonna have here 3 reactions, the y, the x, and moment. Now let's study this problem. You can see this problem, number of R, which means the reaction is gonna be 1, 2, 3, and 4. I have one structure member, so it's gonna be 1 times 3. I'm gonna have 3n is gonna be equal to 3. Now R subtracting 3n is gonna be equal to 1. So this is gonna be indeterminate to the first degree. This is how we figure out the number of degrees. Any questions on this example? Anyone there?
Yeah, I'm here.
Yeah, any questions?
Not for me.
Not so far.
Okay, very good. So the issue again, find out reactions, find out number of separate structural members. For example, if I'm gonna have here internal hinge, I'm gonna say that I have 2. In this case, there is no internal hinges, so I'm gonna say it's gonna be just one member times 3. So okay. Another example. Continuous beam. The reason I call it continuous because it has more than one span. So I have one structural member times 3, so 3n is gonna be equal to 3 reactions. Roller, 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 and this is gonna be a hinge. In each one of these rollers, I'm expecting a reaction in the y direction only. At the hinge, I have in the y and in the x direction. Total reactions here is gonna be equal to 5. So I'm gonna say R negative 3n subtracting 3n is gonna be equal to 2. Therefore, this is gonna be indeterminate structure to the second degree. Why? Because I have here 2. I guess we went through this already and we understand what's going on. That this is gonna be here, if I may go back here to the previous example, indeterminate structure. And the problem is, how would you solve for reactions? You cannot. Because you come here, you take the moment about this point for all the forces, you're gonna have moment and a vertical reaction in the same equation. You do summation of the force in the y direction, it's not gonna work because you don't have this, you don't have that. So having just 3 equations is not enough to solve this problem. So determinate means is gonna be, let's say if I just give you this cantilever and you're trying to solve it or simply support it. Beam. And you should be able to do it with just 3 equations, but in here you cannot really do it. So okay. So what's next? I mean, what can we do about this? How can we solve this problem here? So I'm gonna say to solve this problem, I need to be able to find out deflection and rotation for beams. Now, I guess it is I mean, it's kind of, why do you need deflection and rotation? And how would you do deflection and rotation? I'm going to say deflection and rotation. I remember that we went through this already. We did virtual work, we did conjugate beam method. But in here, I'm going to say, I don't want to really spend the time and do it with the virtual work method. I don't want to do it with a conjugate beam. I'm just going to give you here a table to help you to find out this or to solve this. But just giving you here a few tables. This table is actually, it comes here in the first slide, and this is actually in the back of the book, your textbook. You can see this in the back of the cover. And they give you some cantilever beam, point load at L. And then they give you here the maximum deflection. So this one here stands for deflection. This one here stands for rotation. I know you usually use delta. In delta, we use it as uppercase or lowercase. It stands for deflection, but here it says in this direction is going to be positive deflection, and in this rotation, in this case, is going to be positive rotation. It says here the maximum deflection is going to happen at when x equals to L, and this makes sense. At the end of the cantilever, you're going to have the maximum deflection. It's going to be equal to negative. Why negative? Because deflection is going to be going downwards. I'm expecting deflection to be coming in this direction here like this. So it's going to be negative deflection. Why? Because positive is going to be going upward. So this deflection max is going to be negative. P, which is the vertical load. L cubed is going to be the span divided by 3 EI. And I guess this is also the same equation that I used when I was trying to find out the stiffness factor. If you remember the horizontal, like lateral forces, and we said K, the stiffness factor is going to be equal to 3I over H cubed. So with that, I don't really need to do the conjugate beam, and I don't really need to do the virtual work analysis. I can just look it up from here, from this table, and use it. Let's say, how about the rotation? The rotation at this point actually is going to be coming the other direction. It's going to be positive rotation. This direction is going to be the negative rotation. It's going to be negative PL squared divided by 2EI. It's going to happen at the end of the cantilever. Also, I need to be careful here about units. If you remember, if P is going to be in kips, L, let's say, is going to be in feet, E is going to be in KSI, and moment of inertia is going to be inches of force. So I need to be consistent here when it comes to units. If I need to multiply by 12 or divide by 12, and just so you guys know, the best way, when you keep everything in kips and inches, not kip and foot, it's going to be just much easier when you do kip and inch. And here's the reason. E is going to be already in KSI. I is going to be inch to the fourth. So let me put here some information. I'm going to say this E here is giving KSI, kip per square inches. And this I is giving inches of force. And this L is giving foot. And this P is giving kips. My question is, would you rather have everything at the end when you do the conversion of units to have it in kips and inches or kips and foot? I see here that I have 1 foot to convert. And here I have inches and inches twice. I guess it's going to be much easier if I take this foot, convert into inches before I start my business, my work. And for that, this deflection also is going to be in inches. So everything here is going to be in inches. But if you want to do it in feet, it's going to be okay. But you're going to be spending here more time and more effort because you need to take this inches of force converted, take this KSI converted, and then plug it in this equation. It is much easier when you convert this feet into inch. It's going to be only 1 step versus 2 steps. But what's the good thing about this table? You have the deflection, you have the rotation. I don't really need to go back to the virtual work method or to the conjugate beam method and try to find out this deflection. Another example here. I have cantilever beam with concentrated moment, and it says your deflection at this point is going to be equal to this end here is going to be going up. Why? Because this moment is bending it up. It's going to be doing this. And deflection here is going to be equal to m sub 0 L squared divided by 2ei. Again, be careful with units. So here's a good thing. I need to look for the case. I need to look at my beam here and find out the correct case. Do I have a beam with cantilever with a point load, or do I have concentrated moment? I'm going to go here to the next slide. Or do I have uniform distributed load on the length of the cantilever? And here's the equation for deflection, the end. Or do I have a beam with a point load right in the middle? Or do I have a beam with a point load at distance A, provided the total span is going to be L? Look at the difference between this and this. In this case here, the point load is right in the middle of the beam. In this case, the point load is shifted to the left, or it could be to the right, and it is not really in the middle of the span. It could be shifted right or left, so this A can take any value, and this A can go from 0, right, all the way to L. I can have this very close, this point here, this point load to be very close, or I can have to the right or to the left. And here's the deflection equation. I can use this deflection equation. If you want to find out deflection at point A, for a case like this, you set x equals to A. So in this case, it's going to be L squared minus B squared minus A squared. But if you want to find out deflection for this beam at any other point, provided that P is going to be applied at A, you can just use this equation, and it's going to be B squared, and X is going to be the value that you are interested in finding out deflection at. Meaning, this section here, this X is going to be at the point of interest. This P is not going to change its location, but this X can be variable. You can play with this X the way you want it. If you want to find out the deflection here, or if you want to find it out here, it's going to be up to you. And again, I have also some rotation equations if you're interested in rotation, so you can just use this equation here. So this is nice because, again, I don't need to go back and do it with the virtual work method or with the conjugate beam method. I can just pick the equation from here and use it. So now they are making it much easier for me in this case. I have 1/3 slide. When you have half of the beam is loaded with some uniform load. Now you'd like to find out the deflection here or here at any point, I can use this equation here. And it tells you here, as long as your X value is going to be between 0 to L/2, meaning if you're going to be in this zone, and you find out the deflection here at any point, just use this equation. But if you'd like to find out the deflection for any point from here to there, you need to use this equation. This one, X is going to be greater than L/2, and it's going to be less than or equal to L. One more case, simply supported beam. Point load. How much deflection at any point? Maximum deflection is going to be given by this equation here. Meaning that in the 3 slides, I have standard cases. I'm going to quote here some standard beams. And then in these standard beams, I'm going to have here equations to find out deflection and rotation. So I'm going to call them here pre-solved examples, if you like to call it this way. These are all simple cases, standard simple cases pre-solved for us. So we can just use it for today's lecture and today's method. And what is the method called? If I may go back here, it's called force method for beams. So I'd like to see how this can help me to solve the indeterminate beam. Meaning, this is all determinate. This is not indeterminate. This is all determinate beams. It's going to be simple beams, right? Simply supported beams. Here I am going to have here 3 reactions. I can solve this beam. Same thing, 3 reactions. 1, 2, 3, 1, 2, and 3, 1, 2, and 3. They're all simply supported determinant structures. But I need this analysis here to be able to solve the indeterminate structures. Anyone still recall what does mean by indeterminate structure? Yeah or no? Anyone there?
It's not easy to solve. Unstable, I think.
It is going to be stable. Unstable means it cannot stay. It's going to be collapsing. It is failing. So this system here, is this collapsing? Is this unstable? I'm going to say no, it is indeterminate, but it is stable. The unstable one is the one, let's say that you have two rollers. So if you push it with any force, it's going to just start to move. That's why we call it unstable, meaning it's going to be collapsing under any given load. It doesn't have any resistance. But this is called here indeterminate. And it's going to be indeterminate to the first degree because when you take r negative 3n, it's going to give you a number here, which is number of degrees of indeterminacy. So I have trouble here to solve this, and I need to see how can I solve. Are you guys ready? Yes? No?
Yes.
All right. Good. That's okay. Here's the method. Trying to understand this method here. I got to be very careful. So please stay focused. This can be in my beam, right? The beam is given to me like this. It has point load, give me the length and all the information, EMI and the point load and the whole thing. I'm trying to solve it to find out the reactions, but I cannot because I have only 3 equations and 4 unknowns. So there is no way for me to solve it the easy way. So what I'm doing here, I'm saying, let me take this beam, split it into 2 beams. Are you guys there? You're with me? Yes, okay, I'm gonna have here these 2 beams. So this one is gonna be equivalent to this beam plus this beam. I'm gonna be taking the first support here on the right. Take it out, remove it. So, okay, just remove it for now. I'm gonna say fine. So I'm gonna put the same point load and put it right there. You guys remember the main beam or the 0 system and the 1 system? Anyone recalls the 0 system and the 1 system? Yes? No?
Yes.
Okay, it's gonna be something similar to it. Not 100%. It's kind of similar to it. So I'm gonna come here in the first beam. I'm gonna take this support out and put the load. I say, okay, let me put this out and put the load. Now it's gonna deflect. Now this becomes what? Determinate. So this side is gonna be indeterminate, but this side is determinate. So I force this beam to be determinate by just releasing the support. Just take the support out. I'm gonna have deflection here at B. It says here delta B. In reality, do you have this delta B for this beam? Does it have a value? 1? Are you there? 1.
Yes.
So in reality, do I have any deflection at this point?
No.
So what I have done here, I just took this support out. Now my beam is deflecting. And this amount of deflection becomes delta B. Now, is this determinate? Alina, is this determinate beam or this is indeterminate? Alina? Are you there? Alina?
Yes.
Are you there?
Yes.
Okay, good. All right. Can you answer my question, please? Is this determinate or this is indeterminate? Yes, go ahead, please.
Determinate.
Why? How come it becomes now determinate? I thought that this is indeterminate. Is this determinate or indeterminate?
Indeterminate.
So what happened here? How did I make it determinate?
So it's indeterminate?
I'm asking you. Now you're saying that this is determinate, this is indeterminate, right? And I'm simply asking you what happened to the beam so that now it was indeterminate and now it becomes determinate.
We removed the roller?
So why did I do that? Do you think I had a chance to be able to solve these reactions having this indeterminate, or did I need to do something there?
We needed to remove the roller to be able to solve.
Okay, thank you very much. All right. So what happened? This is again indeterminate, right? And I want to simplify it. So I start here to remove the reason of this indeterminacy. The reason of this indeterminacy that if you look here, I have it is indeterminate to the first degree. So I'm thinking here, if I take this out, I will have here determinate case. And in this case, I should be able to solve for the reactions. And of course, I should be able to solve for this deflection. I'm going to say, how can I solve for this deflection? You say, you simply go to the table, go to the standard beams, and just look for the solution for this. So I said, okay, yeah, let me say that, yes, I'm able to do this. But in reality, this deflection is equal to 0, right? And what's going to bring it back to make it equal to 0? It's going to be the actual reaction that I don't have yet. So actually, this is going to be my unknown that I need to be after. And this unknown here, this reaction, is going to set this back. So deflection at B is going to be equal to 0. And this deflection here, I'm going to call delta prime sub BB. So this delta prime sub BB is going to be positive because this goes down here. If you add it to this negative delta B, they're going to be equal to 0. This equation here, I quote here compatibility equation. This compatibility equation says deflection, final deflection at this point is going to be equal to 0. How can I maintain this? You can say, if I take here this support and remove it and find out the deflection, you can say now this is going to go down, let's say a couple of inches, right? Just throwing here a number for simplicity. If this is going to go here 2 inches and in reality there is no deflection, it means my reaction here, the actual reaction that I can find so far, right? It's going to be doing what? It's going to be pushing this point back so that at the end, total deflection, when you add this, it's going to be positive and this is going to be negative. Both of them, they're going to give me a final result of 0. If this one here, it has a value, let's say 1/4 of an inch, it means I didn't solve it correctly because the amount of here deformation that happened at this point, the deflection, but it's going to be upward, right? This displacement is not really equal to that displacement, but they have to be equal to each other. And each one of us going to be in different direction. When I took the support out, this beam would start to go down. And the only thing is going to bring this point back, point B back from the bottom here, all the way up. It's going to be this force, this reaction. So when I add this deflection, the calculated deflection, to this calculated deflection, in this case, both of them, they're going to give me 0 displacement because this point in reality doesn't go up or doesn't go down. Does it make sense to the concept, or should I repeat? Hey, Brandon, are you there?
Yeah.
Can you help me, please? Can you explain me what I just explained, or not to explain me, explain the group, if you may, please?
So basically, you have an indeterminate structure, and then you make it determinate by removing B. So then it goes down in deflection, and then you get, and then you solve it for C, that figure, and then it will go up. So then it basically cancels each other out to be 0.
Excellent. Very good. Thank you, Brandon.
Thanks.
Very good, Brandon. Thank you. All right. So the question is, how can I find out this deflection? I said, well, this deflection, actually, you find it when you go to the standard beams, like standard cases. I'm going to say, I need to find a case, something like cantilever and things like this, right? Otherwise, I mean, it's gonna be tough. I mean, it's gonna be taking time. I need to go to the conjugate beam or maybe go to the virtual work and spend some time, but I don't want to do this. So I'm gonna go to the pre-solved examples, the standard beams, and just pick the deflection from there and figure it out. Do it like, do the math, do the analysis for it. You can say, how about this one here? Do you know exactly how much is this force? Anyone knows this force yet? Or did we talk about finding it? You're gonna say, no, we don't have it. Actually, this is gonna be your unknown. So I'm gonna say, what happened if I take this beam here, this case, and of course I remove this point load. I'm gonna be taking this beam here and just put one kip. You remember the one system and the zero system? So I'm gonna say, if I put here one kip, I'm gonna go here to the standard beam. I'm gonna say, what standard beam? The pre-solved ones. Let me go back. I'm gonna say, yeah, this one. But instead of the point load coming down, I'm gonna make it here going upward. Can you find out deflection? You can say, yeah, I have an equation for this. For just one kip. So this is gonna be here, deflection for one kip. You guys see this? Deflection for one kip is gonna be equal to that number. It's gonna be FBB. Deflection due to one kip is gonna be equal to FBB. And of course, it's gonna be numerical. Let's say quarter an inch, half an inch, whatever value that you have there. You can say, how many kips I need to put so that FBB is gonna be equal to this deflection, which means to this deflection. You can say, in this case, number of kips is gonna be equal to this deflection divided by deflection due to one kip. Anyone can help me and explain this to everyone? Can you guys help me out?
Wait, you mentioned the number of kips divided by what? I'm sorry. Can you repeat the last sentence you stated?
So what I'm saying is, if I just take this delta B divided by deflection due to one kip, this will give me the reaction.
Okay.
Because let's say, let me put it here in numerical format, just to make it easy. Let's say this delta B, right, is equal 3.5 inches. So you put this beam here, you're going to get deflection of 3.5 inches. This means this force, this actual reaction will bring this back and make it zero, which means delta prime BB is going to be also 3.5 inches, right? Numerically. Let's say I'm just ignoring here the sign. Of course, direction is going to be important. 3.5 inches, right? So this deflection, if I take out this roller support, if I take the support out, it's going to be deflected 3.5 inches. This reaction is going to bring it back by the 3.5 inch up. But if I put here one kip, because I don't have this BY. All what I have is only the 3.5 inches, but I know that at the end, this has to be 3.5 inches from this equation, from this compatibility condition. So I'm going to say, when you look here at this equation, I'm going to say, deflection here is going to be 0.5 inches. So the question is, how many kips would bring this instead of being half an inch to 3.5 inch? Say, well, I need to multiply this by what? Just say 7 times. Why? Because each kip is going to bring this up half an inch. And I need to bring it up by 3.5 inches. So I need to multiply this by 7, whatever deflection, this reaction here. So my reaction in this case, B sub Y is going to be equal to 7 kips. How can I do it mathematically? Yeah, okay, let me look at the equations. Deflection downwards will need to be equal to this deflection upward. So delta B here equal delta prime BB. They're equal to each other. And this deflection here, or for you to get it, you need to take only this beam and put only one kip. And for that, you solve for FBB. If you take this FBB, it's going to be due to how much? Only one kip. Question is, how many kips you need to bring this flat, which means instead of being half an inch, you like to make it 3.5 inches. So we're going to say this deflection is going to be equal to total deflection, which is a 3.5 inch, right? Divided by the half inch. And with that, you get 7 kips. So in this case, in our example, just, you know, this is going to be the total thing is gonna be 3.5 inch, right? Right? So you're gonna say each one kip is gonna pull this up by only 1/2 inch. So I have total of 3.5 inches. So take 3.5 divided by half is gonna be equal to 7. This is exactly what you see here in this equation. B sub y is gonna be the reaction. It's gonna be equal to 3.5 divided by 0.5 is gonna be equal to 7. Are we good? Yes? Vanessa, would you like to explain it to us?
Yeah, so for part G, you mentioned that we need to find FBB, and the way we're going to do that is by using virtual work. And
Yeah.
we want to know, first we want to know how many kips, because we can't just do one, because we know that from the primary structure, the change of B is 3.5. So
Yeah.
in order to find the kips, we would have to divide the 3.5 divided by 5, which would give us 7.
The 0.5, right? Very
Yeah.
good. What's your last name, Vanessa?
Garcia.
Okay. Very good. Thank you. Now I'd like to see numerical example of this. I cannot just let go, right? We need to have now numerical example of this. But before I do this, if you remember, I give you here 2 indeterminate structures. One of them is just to the first degree. The second one to the second degree. So I need us to work conceptually on how can we work on this. Now, in a case like this, maybe I need to take 2 supports out. See what happened here? I just took 1 support out. When I took this out, I convert this into a determinate system. In this case here, I need to take 2 supports to make it determinate system. So here we go. I have here 2 supports that I'd like to take out. So I took them out. Now here we go. Here now this is now our beam, and our beam now becomes determinate. So this one indeterminate to the second degree. This one here becomes determinate because I've just taken the 2 supports out. So I have here how many reactions? 1, 2, and 3. And I have 3 equations. Now I can solve for this. So I'm going to say, well, in a case like this, for this given beam, I should be able to find out deflection at point B and deflection at point C. What is point B and C? I'm going to say this is the location of the previous support that I just removed out. Let me find out deflection here due to what? Due to the given loads. I'm going to put here some load, and this load here, B sub y, is going to be actually the force that I need to put there so that this point is going to be going up, back, so that I'm going to have here 0 deflection. I'm going to say, how about this point C? I'm going to say, you know what? Let me put here a reaction. So this reaction, you can say, is going to be going upward, downwards. It doesn't matter because at the end, you're going to have positive or negative, right? And these 2-point loads, once you put them, each one is going to be separate. They're going to bring back this deflection of points B and C to be equal to 0. In a case like this, I need to bring a beam like this and put only 1-point load here, 1 kip, and bring this beam here and put 1 kip and find out deflection here and there, find out deflection here and there, and then form my equation so that final deflection at each one of the supports. So this one is going to be a support B and this one is going to be a support C to be equal to 0. So at the end of the day, deflection at point B and C needs to be equal to 0. And this is how I came up with this 2 equations. So it seems here I'm going to have more work to do because it's going to be indeterminate to the second degree. And it seems here that that was very simple, that I just took 1 support out and then I put some force here, the 1 kip, is able to find out FBB, which means deflection due to only 1 kip. And with that, the reaction is going to be equal to the total deflection at this point, divided by the deflection caused by 1 kip. So, okay, good. I'd like to say an example. An example is going to make it easy. Can be taken exactly the same problem. I'm going to say, okay, here's the problem that I started with, the first example. I'm going to take this exact example and solve it. So, okay. Here's my example 10.1. It says here, determine the reaction at the roller support B. Where's the roller support B? I'm going to say right here. of the beam shown in this figure. And it says here, EI is constant, meaning given this EI value or just not given it, it's gonna be okay with me. I don't really need to have the exact value for EI because at the end of the day, I can cancel it out. I can show you how. So the main beam given, it says here, total length is gonna be 12 meters. Right in the middle, I have 50 kilonewton as a point load, fixed roller. Okay. Here is the first structure. How can I convert this and make it determinate? Gonna be taking this support out. Taking this support out, here's the beam, and this is the way it's gonna deflect. First, I'm gonna have here some curved section of the beam, and then after that, the beam is gonna be going straight. I may zoom in here. It's like a curve, and then after that, it's gonna be straight. Why this gonna be straight? Because there is no loading here. When you have loading on the section of the beam, you're gonna start to bend it, so it's gonna see some curvature. And this part from this point here, C to B, is gonna be straight. I'm talking about this section here. From here to there, it's gonna be straight, and from here to there, it's gonna be curved. Okay. And then I'm gonna say I need to have another beam, like the one system, if you like. I'm gonna put here a point load and find out how much deflection is gonna be going upward to resist or to counteract the effect of this having no support at this point. So, okay. How my equation is gonna look like? Yes, a deflection that you get from the primary structure, like the main system, is gonna be equal to delta B. Like in our example, I said here 3.5 inch in the previous example, numeric 1, is gonna be equal to the reaction, total reaction, multiplied by the amount of deflection here that's gonna be caused by one kip only, which is this FBB. I'm just repeating exactly the same conceptual problem that we have done. So look at how can I do here deflection at this point, at point B? And do I have a method to do it or I don't? So I need to go back here to my standard table, the standard beams. Just need to look at them. So here's the beam that I'm working on. This from our example. It shows here 50 kilonewton, 6 meters. I need deflection at this point, not at this point C. I need deflection here. The only case I was able to find it looks like this. This is not like this. This is different. Why this is different? This one here, I have the point load in the middle of the beam, but this one here, I have the point load at the end of the beam. It's not exactly the same. And I couldn't find any case at which I have this point load is gonna be right here in the middle, or at some point, and I'm looking for deflection at the end. So what I'm saying is, if I may consider this to be my cantilever, like this is gonna be the same, right? The length is gonna be only 6 meters, and the point load is gonna be 50 kilonewton. I should be able to solve for the deflection, but this deflection, if I solve for it, is gonna be the deflection at that point, correct? So this deflection is gonna be right here for this curved section of the beam. And then after that, I'm gonna have a straight line. Gonna zoom in here. Now the total is gonna be delta B. And from here to there is gonna be delta C. Look at this. If I go here straight, this is gonna be delta C from this point to that point. So I have an equation for delta C, and the equation is gonna be right here. It's gonna be this equation, PL divided BL cubed divided by 3I. And L in this case is gonna be only 6 meters. And between point C and B, I'm gonna have a straight line. And they have this rotation. And this amount of deflection from this straight line, the horizontal line, to that point at the end, this is gonna be equal to the rotation times the distance. So if you may here, I can divide this into 2 sections or 2 segments. Here's the first one, which is the same as delta C, right? can say this here equals to delta C. It's gonna be only from this point to that point, right? Can I have here another component of this delta, which is from here to there, and this one here is equal to, if I may put it here, the rotation, so it's gonna be equal to theta, right? At C times 6 meters. Why 6 meters? Oh, it's gonna be because the distance from where? From here to there. If you have the angle of rotation, which means the slope, you take the slope of this line, multiply by the length, it's gonna give you this displacement. So the first component of displacement is gonna be taken from delta C, from the equation. Which equation? I'm gonna say from this equation. Second component is gonna be based on the rotation. And the good thing is I have also an equation for the rotation. It is also given to me in this problem. So I'm gonna say total deflection of point B due to this 50 kilonewton at the midspan is gonna be equal to the following. I'm gonna say two components. Here's the first component, delta C, plus the second component due to rotation. Okay, let me look at this. It says here delta B equals total deflection at the end of the cantilever is gonna be equal to delta C, displacement in the middle, which is this deflection, plus theta at C times 6 meters, this distance here. Here's the first component, which means delta C. I can say this is gonna be exactly the same as this, right? Delta C. How much is this delta C? We can say PL cubed divided by 3R. Now, L in this case is gonna be actually L over 2 of that beam, which means this L over 2 is gonna be only 6 meters. It's not gonna be the 12 meters because I'm considering only 1/2 of the beam. Plus the rotation, here we go. Where's the rotation equation? I'm gonna say PL squared divided by 2EI. I'm gonna say PL squared. Now L again is gonna be what? It's gonna be this L over 2, the 6 meters, right? It's squared divided by 2EI times this length from here to there times L over 2. So this L over 2 is gonna be actually this length, and this L over 2 is actually this length. Another problem, I may give you this 9 and 3. So in this case, this is gonna be the 9 meters, and this is gonna be the 3 meters, right? So this L over 2 is gonna be the distance from here to there, and this L over 2 is gonna be from here to there, from A to C. This L over 2 is gonna be also again L to C. Following?
I have a question.
Yes.
So why in the second one with the rotation, why we multiply it like for the half of the length? However, for the first part we didn't.
Can you repeat again, please? I was unable
Like
to hear you.
for the rotation, like
For the what?
type for the rotation, like for the second part of the equation, we
The second?
multiply it by we multiply it by half of the length. But
Yes.
however, the first part we didn't. Can you explain again to me why?
Okay, sure. Okay. Let me call this. I'd like to rename this. I'm gonna call this L1. Are you okay with that?
Yeah.
Okay. And this section of the beam, I'm gonna call it here L2. It just happened in our example that L1 and L2 is the same, right? But in many other cases, it will not be the same. So I'm gonna say here, let me look at this equation. The first equation here is about a cantilever. So I guess this 6 meters just happened to be L over 2 of that beam, but in this case, I'm gonna say, you know what? This section is what? This term, I say this actually L1, correct? PL cubed divided by 3I for this cantilever. And this length actually, which is the same box, I'm gonna put another box here, correct? This is actually L1, right? The rotation for the first segment.
Okay.
And this L over 2, the last one, is actually L2. Because you take the rotation time the distance, time this distance here, the 6 meters. So it's going to be actually L2. Does it make sense now?
Yeah.
Okay, very good. It's good that we put in terms of L1 and L2. So if you have two different lengths, you should be able to work it out here. You can say the math here is going to be very simple, right? You do P, you do L cubed, and we said that we don't have here EI, and we don't really need it. We can just solve the whole thing here in terms of EI. Because you know what? EI can cancel out, is going to get canceled out when you compare it to the other equation. So I'm going to say here, just because I took this support out, now I run the analysis, find out deflection turned to be 9,000 kilonewton meter cubed by EI. I understand that. You know what? It's going to be just 9,000. Forget about this EI. I'm going to take the same beam. Put the 1 point load at the end of the cantilever. Meaning, here's the cantilever. One point load. And this here is going to be equal to 1 kip. Or 1 kilonewton. All right? How much deflection would I get? Upward. You can say, let me try. This could be the same equation. And actually now this L becomes what? You can say, oh, this could be the same, the whole thing. It's going to be 12 meters, right? This is going to be 12 meters. Now, this amount of deflection that you get here is called FBB. F sub BB, which is this one here. Is going to be equal to PL cubed divided by 3I. But in this case, the L is going to be 12 meters. I have here 3I. So what is this for? I'm going to say this is going to be the amount of displacement that you would get upward when you apply only 1 kip. Look at the force here, 1 kip. So if you put here, if you take the roller out and look at deflection, total deflection is going to be 9,000. If you put just 1 kip pushing upward, you'll get here 576. Now I guess the reaction here is going to be equal to 9,000 divided by 576. I can look at this. Look at this. 9,000 divided by EI. Someone's going to say, where's the EI? I'm going to say it's just going to get canceled out because look at this equation. 9,000 plus BY times 576 divided by EI. You should be able to cross out EI and EI. Just cancel them. So I don't really need the moment of inertia as long as the moment of inertia is constant. It's going to be the same. So based on this equation, I'm going to say here, primary system. You put the loads, you get deflection of 9,000. You put 1 kip to push up, you get 576. How many kips it needs to bring this back to be flat is going to be equal to 15.6, which is 9,000 divided by 576. You see, now you have this solved for you, right? Now you have this reaction, 15.6 kilonewton. You have here 50. How much is this reaction here? You say summation of the force on the y equal to 0. How do you do it? You say, well, I have here negative 50 plus 15.6 plus, you can see here, the y direction is going to be A in the y direction equals 0. Can you solve here for AY? Yeah, you solve for AY is going to be 34.4 kips. Can you find out this moment? You can say take the moment about this point equals 0 for the whole system, right? See, you should be able now to solve the reactions. I'm not going to teach you now how to do reactions. You guys are very good. I mean, they are very good in solving reactions. Can you do the moment diagram? You can say, yeah, you should be able to. At this point, it's going to be 0. At this point, it's going to be positive. At this point, it's going to be negative, which is 112. You should be able to develop this moment diagram. Questions before I move forward?
Professor?
Yes, go ahead.
So in this example, when you took the support away, you drew the reaction upwards, but in the example before, when you took away 2 supports, you drew the reactions downward. Is there a reason for that, or is that just a choice?
It's a choice.
Okay.
And let's say that by mistake, right at the beginning, I have the wrong estimate. I decide to show it downwards, but it was supposed to be upward. What's going to happen? I'm going to have negative answer, which means the direction assumed is incorrect.
Okay.
Make sense? Yes.
Yeah.
Okay.
Thank you.
Good question. Thank you, Sanjay. Any other questions? You're good? All right. Another example. This structure here, indeterminate. Hinge, roller, and then another hinge. I don't have any forces here in the x direction. So to make this kind of determinate, just remove the support. It says here, draw the shear diagram and moment diagrams for the beam shown. Support B is going to go down 1.5 inches. It's going to settle 1.5 inch. Due to what? Let's say, just imagine that you have a building here, or let's say a bridge. This bridge, it had 3 supports. We call this abutment. The first one, let's say the last one, you call this abutment, right? And then you have like a column in the middle. Sometimes because of the soil condition, maybe the poor design of the foundation, this is going to be going down like this. When this goes down, it's going to be pulling the structure with it, the bridge itself with it, right? So we call this settlement. This is why it says here, the support at B settles, which means it's going to be moving down. By how much? It says 1.5 inch. So you're taking this beam with you down. When you're taking it down, it means that you're going to be causing more compression on the top. You're going to be changing the moment distribution, right? And they give you E, and they give you moment of inertia I. You say, okay, go ahead and solve, draw the moment diagram and the shear diagram. You say, this is now something new. Settlement, I didn't hear about it, and I need to include in my equation. So now this is going to be the actual beam, right? I need to do the primary structure like the zero system. If you remember the zero system, I'm going to be taking this support out and just find out deflection at this point B, right? At the support when I take this out. I'm going to come here, I'm going to say, you know what, to solve this, I'm going to put here one kip. Find out this deflection FBB due to 1 kip. So if I put here 1 kip, right? I can solve out for this FBB due to 1 kip. But I can't say how many kips are needed to bring this back to 0, because this is actually, it doesn't have 0 displacement. This support actually moves down. It moves down by 1.5 inch. So now I can rewrite my equation. Instead of saying delta B plus the reaction at B times FBB, it's not going to be equal to 0. It's going to be equal to some settlement, some movement at the support. Where is this 1.5 inch coming from? You can say coming from here. So what I did here, I just changed my equation a little bit. So when I have here support settlement, well, what I need to do is to allow it in my equation. So instead of having this reaction here to bring back this point B here to the original location at 0 point, actually it cannot, because I have an issue with the soil below this. It's going to be just pulling it down. And once it pulls it down, this needs to go down with it. So it's going to be deflecting this way. If you like, it's going to be doing something like this, right? So you cannot really have 0 displacement here. You're going to have 1.5 inch. The good thing about this type of beams that they have it pre-solved for me. They have here, if you look here at this beam, this is going to be from the standard pre-solved beams. I have the point load at point A, not in the middle. Yes, say, well, this point here is not in the middle. Look at this beam here. This point here is going to be at 12 feet, which means at the quarter point. 12, 12, and then 24. It is true that the previous support used to be in the middle, but in this here, in my analysis here, what I'd like to do, I want to find out, in my example, deflection at L/2, when I have the point load at A, which means at 12 feet. This is what I need to do. Here we go. In my analysis here, I want to find out deflection at B when the point load is going to be at 12 feet from that point. But the deflection I'm interested in is going to be at B in the middle. And where is this B at? I'm going to say it is going to be at 24 feet from the right or to the left. I have an equation that says deflection equals negative P, which is this point load, times B, which is this distance. In this case, is going to be 36, right? Times X, and the X is going to be equal to 24 because X is going to be to the point of interest. So actually this point is going to be all the way to here. This is going to be the X location, right? It's going to be like this. So I'm going to say this is actually the X distance. This is going to be equals to 24. Now let me look at my equation. Just copy the equation. It's going to be the same equation. Now let me look at the values. The point load P is 20 kips. Yes. See this 20 kips? It's correct. B lowercase here, which is this location of the point load from this side, is going to be how much to the point load? From here to there. Can someone help? It says here 12, but I thought it can be 36. Am I correct? How come they're using it like this? You see, yeah, you can do it if you just look at this from the other side. If you mirror this face or you mirror this example, you're going to get exactly the same answer. Does it make sense? Yes? No? This A and B, you can just flip them. You can switch them. Am I correct?
Professor, can you please repeat this again?
You're cutting off.
Can you please repeat this again?
Can I repeat again? Okay. Yeah, I repeat. Yes, absolutely. I start here to put the variables. I said the X is going to be equal to 24, right? Based on this, the location of the point. And I was thinking that this is going to be A, which means this A is going to be 12. And B is going to be equal to 12 plus 24, it's going to be 36. I start to look here at the numbers, and then I find out that they didn't do it this way. So I'm wondering, what have they done? What they have done, you just mirror this shape. So you can have here, if you like, you can have here the beam, you just look at it from the other side. You just mirror it. So A is given to the right, B is given to the left, and X is given somewhere from this point to that point. And here's the reason that they are doing it this way. This X value, it needs to be between 0 and A. Meaning, if I'm going to be taking this beam here, now I need to set the variables. Same variables that you look here at, I need to draw it here. So I'm going to say, where is A? It says when X between 0 to A. I said, okay. So where's X? X is going to be here, which means this is going to be A. Now, what is A again? A is going to be from here to there, correct? This has to be A, because X in this equation, it needs to be between 0 and A. And this give you my X value, right? So I'm going to say, here's the X value, the 24. And A equals 36. How about B? Let's say here's B. Let's give you this. I'm going to say here B equals 12. We're good. Total length L. You say total length is 24 plus 24. You say L equals 48 feet. How about P? The vertical load. You can say 20 kips. Now let me look at this equation. It says P, here's the 20 kips. B, 12 feet, right? Say this is going to be that, right? X, 24, it's right here. Divide by 6L. What is L? How much is L? 48. Okay. And EI, yeah, I have the EI, but you can keep it to the end. Now it says L squared. Yes, L is 48. B squared is going to be the 12. And X squared is going to be the 24. Direct substitution now of values. This is okay. Here's deflection due to what? Give me deflection due to, can someone help me here? Deflection due to what? The primary structure. It means when you take the support out, it's give you total deflection that happened at this location. And they just decide here to leave it in terms of ER for simplicity. Okay. Now, if you take this system here and then you come, you put like a beam like this, you put one point load like this going up. Let's say, you know what, let me put it here. Here's give you my beam. Right in the middle, I'm gonna put here a point load. I'm gonna say, I need to look for an equation like this, which means this equation. This is different from this equation. So I'm gonna say, you know what, this is now slide number 14. Let me go here to the front. Maybe slide number 3. Is it number 3? Yeah, here we go. Here's my equation. PL cubed divided by 48 EI. Point load in the middle of a simply supported beam. And deflection right in the middle is going to be equal to PL cubed divided by 48 EI. So I'm going to go here. Here we go. PL cubed divided. Yeah, this is going to be the same equation, right? We saw supports here and there. Here is P, 1 kip. Just going to be applying 1 kip. 48 cubed, the span cubed divided by 48 EI. And here we go. If there is no settlement, I just take this value divided by that value. But in this case, I need to rewrite my equation. It says 1.5 inch. If you remember, this gives you equation number 1. 1.5 inch equals deflection at B plus the reaction multiplied by vertical displacement due to 1 kip. So, okay, here we go. 1.5 inch. All what I did here, I took EI multiplied by here. You see here, when you write the equation, you can just take this EI. So let me put this down. I say this here's gonna be EI. You can divide each one of this displacement by EI, or you can just take it multiplied by the 1.5 inch. Go back to this equation. This equation here is gonna be in terms of EI divided by EI. This one also divided by EI. So I can just take E and I multiplied by 1.5 inch, and this is what happened. So I'm gonna put here a note. This term is going to be actually E times I. Okay, it's going to be equal to the 31,680, and you see here EI vanished. It's not there anymore because I multiplied by 1.5 inch. Plus BY times the 2304. And also I need to do kind of maybe adjustment a little bit for units. And what is the reason for this? Because this here is going to be an inch. This is going to be an inch, so I need to convert here each foot into an inch, which is much easier. So usually don't try to convert to feet. Please usually convert to inches. Solve this equation. The reaction here is going to be 5.56 kips. So, okay, good. What was your assumption when you put this point load? This reaction here, if you remember, this reaction is positive, right? For this deflection is going to be positive, which means in my assumption, I assume that the beam is coming this way, right? And the 1 kip is coming this way. It's going to be the direction of my reaction. This is why I'm getting here positive deflection, right? You see, this is going to be positive. When I put in my equation, I find out that I have negative value, meaning that the actual direction of the reaction is going to be acting upward. So I was going to say, is upward is going to be positive or negative? I'm going to say, you know what? When you assume the deflection is going to be coming this way, right, and you put the point load like this, the analysis is showing you that it's going to be going upward, the actual reaction. It's going to be opposite to your assumption. So if you assumed that the beam is going to be deflecting downward and that your reaction here is going to be going downward, now you need to know it should have been upward. And this is a question that Sanjeev asked about, right, Sanjeev?
Yeah.
Okay, very good. What do you do after this? You say, okay, here's my beam. This gave me the force that I just solved it for. I have 20 kips, I have 2 reactions, right? Now, at the beginning, all what I have is just this. And I have this now. Now I should be able to solve for these 2 reactions. How can I do this? Now this becomes determinant system. Now I can take the moment about this point. You say 20 times 12. negative 5.56 times 24. I'm gonna say negative whatever reaction C sub y times 48. And for that, I should be able to solve for C sub y. Exactly like what you're looking at. Here's the equation. Now solve for Cy, do summation of the force in the y direction, you solve for Ay. Now you have the two reactions. Now you solve the beam. Next, you do the moment diagram and the shear diagram. Since you solve for reactions, I'm gonna say here's the shear, here's the moment, and I don't think that you guys need my help to do the shear diagram and moment diagram. Very important note here that you guys know that we have a TA who's doing review for you guys, and some of you start to go and see him. His name is Rami, and he is in room, is it E11 or E13?
E11.
E11, very good. All right. I urge you guys to go there and check with them about moment diagram and shear diagram. I know that this is something that you studied back in the statics and mechanics of materials. And some of you maybe forget the way it works or how to do it. Please be sure that you go sit with them, because you see, once I get to a slide like this, I'm going to say reactions, shear, moment. I'm not going to spend any time on it. And if you feel that you struggle with this, or maybe you need someone to refresh your memory with this, and you'd like also to exercise, I'm advising here you guys to go there and sit with them. Anyone knows his schedule? Yeah. Can you please? Yeah. Can you please put in the chat room?
Yeah.
Yeah. Please put for everyone. What is the schedule? I really urge you guys to go and sit with them and see. It's very useful. This is gonna be good investment for your time. Now, any questions before I leave and let you go? Be sure that you sign out. I'm here to answer questions, and please be sure that you sign out same way you type your name in the chat room. Was anyone here and I didn't call his name, I did not register it here? Jorge, Danny, Nether, Aaron, Louis, Christian?